we have one population, and then based on this population, we randomly select a sample, and then based on this sample, we can get a confidence interval. We can also compute a hypothesis test. Right, so all of these steps are based on one population. But what if I have two populations? What if I want to compare these two populations? Which population has larger population mean? The other one has smaller population mean. Which one is larger? Right, so then think about the whole process. We say if we have one population, then we randomly select one sample from that population and then get the hypothesis test and the confidence interval. But now I have two populations, so of course I should select one sample from each population so that I have two samples, right? Okay, so now let's look at this example. We say Vivian has a successful app which runs on two common operating systems, right? We call it System A, System B in the smartphone market. All right, and she wants to decide in which system to build the new features by determining which system has users that spend more money. Right, so we say, oh, I want to compare which system has the users spend more money. Right, and then to compare these two systems or compare these two populations, she randomly selected samples users from each operating system and measures how much money they spent on the app in the past month. All right, then I should have two samples, right? So we call sample A, sample B. One sample from the users who use the system A, one sample from the users using system B. All right, so now I have sample 1. I have sample 2. Right? Okay, now based on each sample, I can get some basic information about this sample, right? So I can get what this is the sample mean of system A, right? The sample standard deviation for system A, the number of users, which is our sample size of system A, right? Similarly for the another sample, sample 2. All right, so based on these two samples, I want to compare which system should I use to build the new features. Right, that means I need to decide which system has the users spend more money. That means I need to compare the population mean A and the population mean B. I want to compare it is larger than that, less than the mu B, or maybe just different from the mu B. Right, so then before we do any hypothesis test, if we look at these two samples, we say the mean of sample 1, sample A is 13, the mean of sample B is 10. So it looks like the system A has the users spend more money than the users using system B. But you see the difference is 3, right? So is this 3 a significant difference? That I can make the conclusion that population A has larger mean than B, or this 3 is just a random fluctuation. That means if this difference is not big enough to say that the population A is larger than population B. For example, if I randomly select another two samples, maybe I have a larger sample mean in B than the money spent by the system A. Right, so we want to know whether this difference is a significant difference or is just because of the random fluctuation. All right, then we need what? Of course, we need our hypothesis test. Right? Since we still have the fresh memory, let's just think about the whole process. right? So we say, actually, I have A and B. Actually, I want to compare these two for this relationship, right? Based on what we learned for, let's to open the old one, right? So we say for the hypothesis, for the null hypothesis, we have the population parameter equals to the claimed value, right? For the alternative hypothesis, we can have three options. We can test the left tail, which is less than the claimed value, right tail larger than the claimed value, not equals to the claimed value. Right, so that means this claimed value is the value we want to test about, right? But now we have what? We have two population means. I don't know the population 1, I don't know the population mean 1, I don't know the population mean 2. So of course, this is not the claimed value we can test about, right? We need a detailed value so that we can put into the formula to calculate the test statistics. The point is how we can convert this kind of hypothesis to another kind. To the kind that we are familiar with. We say, for example, if we want to test mu1 larger than mu2, if we subtract mu2 to both sides, is that just we want to test the mu1 minus mu2 larger than 0? Right? They are the same thing, right? So in this case, if we change the format, at least to the right here is a detailed value we can test. We can call this is a claimed value that we want to test about. The left side is the difference between the two population means. We call this is another kind of population parameter. It's just another the difference between the two population means. We call it is the delta. It's the triangle. We call it is delta. Right. So now this hypothesis, this alternative hypothesis can change to delta larger than 0. Right? So delta here is the difference between the two population means, and 0 is our claimed value. Is that just similar with what we have before? Right? That means this mu0 is just set to be 0, and then this mu here we just gave another name, which is the delta, which is about the difference. So we can test delta equals 0, alternative hypothesis can change to delta larger than 0, right? So that means it will be the same format as what we learned before. Similarly, right, if we want to test whether the mu1 is less than mu2, we can change to this format, right? And then again, mu1 minus mu2 is called delta, so we can test about delta less than 0. Similarly, we want to test whether these two population means are different or not. Then we can test whether the difference is not equals to 0. So it will be delta not equals to 0. Right? And then of course this is the alternative hypothesis. The null hypothesis is just a delta equals to 0. Right, so now the idea just changed back to the chapter 12, to chapter 13, right? So we have a population parameter we want to test about, and then this 0 is our claimed value, and then we can make this hypothesis test. All right, okay, so now let's try this hypothesis test. We call this is a two sample test because we have two populations, and then we have two samples from each population, right? One sample from each. So totally 2 samples, right? So this kind of hypothesis test, we call it is the 2-sample test. Depending on whether the population standard deviation sigma is given or not, we have the z-test or t-test. Very similar, right? Okay, so now the step 1, again, step 1, state the hypothesis, right? So we have already talked about this kind. We say we want to compare these 2 population means. I want to know whether mu1 is larger than mu2, less than mu2, or not equals to mu2. Then if we subtract from both sides, we have this kind of hypothesis. But what if I want to not only compare these 2 population means, I also want to test whether one population mean is larger than the other one by some specific value. For example, I want to test whether the weight of men is larger than women by 10 pounds averagely. That means I not only want to test whether the man's weight is larger than women's weight, I also want to know by what amount, right? So I think the man's weight is larger than women's weight by 10 pounds averagely. So that will be man's weight minus the women's weight by 10 pounds. Right? So men is larger than women by 10 pounds. So this 10 again is our claimed value. Right? So this is again our value we can test about. This 0 is a special case that we don't care about whether we don't care how much the mu1 is larger than mu2. We just want to compare these two. Right, but if we have a specific value we want to test about, we can also test about, we call this claimed value, we call it is delta 0. We use delta 0 as our claimed value. Similarly, if you can recall, in our previous chapter when we talk about the hypothesis, we call what? We call our mu0 as the claimed value. P0 as our claimed value. Now we have another kind of claimed value. We call it is delta 0. Right? So this is the general format for comparing the 2 population means. If we don't care about how much the mu1 is larger than mu2 or less than mu2, then this delta 0 has a specific or special case. That's the delta 0 is just a 0. Got the idea? Good? All right, so now we kind of convert the case comparing 2 population means to just the case that we have already learned in the previous chapters. Then you can think about next step. What is the next step? Again, check the assumptions and then use the formulas to calculate the test statistics again, right? Okay, so now next step, check the assumptions. Right. So we say we want to test about the population mean. We say for testing about the population mean, we need to check the assumptions, independent assumption, normality assumption, right? So we say for independent assumption, we need to check what? We need to check whether the sample is randomly selected, whether the 10% condition is met, right? So when we have one sample, we want to test whether the individuals in each sample are independent of each other. We don't want them to be related, right? So that's why we need to check whether these observations are randomly selected, whether your sample size is not too large so that the individuals still independent of each other. Again, Now we have two samples. That means for independent assumption, within each sample, you need to check whether this sample is randomly selected, whether this sample size is less than the population size, right? 10% of the population size, right? So in this case, actually, we are testing about whether sample size 1 is less than 10% of the population size 1, and sample size 2 is less than 10% of the population size 2. So actually, you need to check it twice for each sample. Again, this one you need to make sure your sample 1 is randomly selected. At the same time, your sample 2 is also randomly selected. So actually you need to check this independent assumption twice for each sample. Okay, so here I think this assumption is easy to understand. Next one, think about now I have two samples from the two populations. I want to make sure everything is independent. Another thing we need to check is we need to make sure the two samples are independent of each other. Not only the observations in each sample, we want to make sure the two samples are also independent of each other, right? So for two sample test, we have one more assumption to check. We have two independent assumptions. One independent assumption is within each sample. You check the randomly selected 10% condition. Another independent assumption you need to check is whether these two samples are related with each other. Right, so here for the second assumption, you don't have any specific, for example, this kind of formula to check, right? So what you need to do is just think. Right, so for example, if I want to compare whether there is difference of average height between the male and female in Ohio, then if I select two samples as group 1 with husbands and group 2 with their wives, are these two samples independent of each other? Of course not, right? So these two samples are not independent of each other, then this assumption is not checked. Right, so for the second assumption, second independent assumption, you need to think about it, right? There's no way for you to check by some formulas or by any use. You just need to think about it. All right, so similarly, once we check the independence, we check the normality, right? So remember, all right, so remember for one sample test, we say for the normality, what do we want to test about? Testing about the mean. We want to test whether the sample size is larger equals to 30. That means if it is larger than 30, we can apply the central limit theorem to say the sampling distribution is normally distributed, right? And now we have two samples. That means we need to check both samples. We need to check the sample size 1 is larger than 30. At the same time, the sample size 2 also need to be larger than 30 so that we can apply the central limit theorem to check this assumption. Got an idea? All right, so now think about the assumption part. We have one more assumption. Right, we have independent assumption, which is exactly the same with what we did before. We just need to check twice for each sample, right? In the end, we have another independent assumption. We need to check whether these two samples are independent of each other. And then similarly for the normality assumption, again, we need to check whether the sample size is larger than 30 for both samples. All right, if these three assumptions are all satisfied, then we can use the formula to calculate the test statistics. All right, so now here is the test statistics formula. It looks like a little bit complex. Let's look at details. All right, so let's recall a little bit from the one sample test. So for one sample test, we say we have two cases, right? One is when the population standard deviation is given, one is with the population standard deviation is not given, right? So again, for our two sample test, right? So again, two cases, we say if the sigma 1 and sigma 2 population standard deviation 1 and the population standard deviation for the population 2 are both given, then we'll have the z-test statistics. Another one, if either of these two are not given, or both of these two are not given, then you have the t-test statistics, the same idea. All right, so now let's look at this z-test statistics. We say the z-test statistics, when we have the one sample test, we actually have the x bar minus mu 0 and sigma over square root of n. Right, so we call the bottom here as the standard deviation of the sample mean. All right, so now we have two samples. We want to test about the difference between these two population means. Think about what we can have for the z-test statistics for testing about the mean, testing about the difference between mu1 minus mu2. Right. So now think about the first thing, x bar. What is x bar here? X bar is the sample mean, right? So we say we use the sample mean to estimate the population mean. That is why we use the x bar minus mu0 here, right? Similarly, for two sample test, what would you do or what would you use to estimate the difference mu1 minus mu2? What do you think? Anyone? We say for one sample, we use the x bar, which is the sample mean, to estimate the population mean. Now we want to test about the mu1 minus mu2. Then what you can use to estimate mu1 minus mu2? Abby, what do you think?
I'm not sure.
Not sure? Okay.
Would it be the delta of the triangle?
Will be the delta. Let's see. Let's come back. What is delta? Delta is just a mu1 minus mu2. So actually this delta is a population parameter. Right? So actually this is the one we want to estimate. So my question is what you can do to estimate this delta. What you can do to estimate this mu1 minus mu2. Anyone?
Use the average.
Use the average, right? We use the sample means for the difference between these two samples, right? So we say use x bar to estimate the population mean. Now we want to use the difference between these two samples to estimate the difference between these two populations, right? So to estimate the difference between these two population means, we use the difference of the sample means, right? Okay, now minus mu zero. Here in the formula, we use the mu zero for one sample test. What you can do or what you can use to replace this mu zero if we want to test about the difference. What is the mu zero again? Mu zero is the claimed value or hypothesis. So what is our claimed value in our hypothesis? Delta zero, right? So this is the value we want to test about when we test about the difference. Right? So that means we can replace this mu zero by delta zero, our claimed value. And then divide by the standard deviation. Now this is the standard deviation of one sample. Now I want to calculate the standard deviation of the difference between these two. Right? And then that will be the test statistics for two sample tests. Right, so that will be our formula here. Here I use the y1 bar and y2 bar instead of the x1 bar, x2 bar. They are the same thing. They are just the sample means. Just in case I don't want you to get confused with one sample test and two sample tests, right? So we just use y bar instead of x bars. Right, so both of these two are still sample means. All right, so now the only thing left will be the bottom standard deviation of y1 bar minus y2 bar. Right, so what is the standard deviation? Some student ask me that what's the difference between the margin of error and standard error? What's the difference between these two? So what is this? What is the standard deviation first? Regularly. We say if we have a sample, if we have a data set, what is the standard deviation? Standard deviation just a way to calculate their variations, right? How large variation they have in this data set. All right, that means if I have one sample, I have one kind of variation. But now I have two samples. And that means that the variation will be kind of doubled, right? So it will be one standard deviation kind of plus another standard deviation. But actually we cannot do the summation like this. We need to square them to get a variation and then square root to get the standard deviation of the two samples. Right, so now let's think about from the beginning. We say the standard deviation, if we have one sample, what is the standard deviation? The standard deviation for one sample, we say is sigma over square root of n, right? And then we say the variation of one sample will be just the square of the standard deviation, which is sigma square over n. This is for one sample. Now I have two samples together. That means the variation of the two samples will be one standard deviation, one variation, one, plus the other one. Right, so this is the variation. Next, square root, I get the standard deviation of these two samples. Right, so you don't need to understand here. If you don't understand, that's fine. I just want you to show you where does this formula come from, just in case if in the future, if you want to derive the formula for 3 sample test, 4 sample test, it will be the similar idea. All right, so you just have this formula, right? So we say when we have two samples, the standard deviation will be sum squared, sum together, and then square root, which is the standard deviation. All right, we say now we have the complete formula for the z-test statistics, right? We have the y bar, which is the difference of the sample means minus our claimed value in our hypothesis, divide by square root of sigma 1 square over n1 plus sigma 2 square over n2. Put them together. Our z-test statistics equals to the difference of the sample means minus our claimed value in our hypothesis divided by sigma 1 square over 1 plus sigma 2 square over n2. That will be it. Right? So in this formula, we say once we have the samples, two samples, we have the two sample means. So we have this part, right? Once you state the hypothesis, you know the delta zero in our hypothesis. And then sigma 1, sigma 2 are both given, and you have the sample sizes. So the z-test statistics can be calculated. Right? And then similarly, very, very similar idea. We say when the population standard deviation is not given, we do not have the z-test statistics. We have the t-test statistics. Right? For the t-test statistics, everything to the top is the same. We still use y1 bar minus y2 bar minus our claimed value. Divide by, now we don't know the population standard deviation. We use the sample standard deviation instead. Done. All right, so that will be the t-test statistics when the sigma, both population standard deviation are not given, or either of them not given. Is that easy? Right? So it's just a kind of modified format of our chapter 12 hypothesis, right? Okay, so here I just have a note say, remember when we state the hypothesis, we have a special case, right? So we have this special case when we only want to compare these two populations. We don't care how much one is larger than the other one. We just want to know who is larger. Then this delta zero is just a zero, right? Otherwise, I can compare one is larger than the other one by what amount. Then this delta zero has a different value, right? Okay, so then once we have the test statistics, what will be the next step? Use the test statistics to find the p-value, right? So it will be exactly the same steps, right? So for the z-test statistics, let's review a little bit, right? So we say for the z-test statistics, how you can find the p-value. We say if you have a right tail hypothesis, that means if you have mu1 minus mu2 larger than the delta zero. If you have a right tail hypothesis, what is your p-value? You go to the standard normal table, find the probability to the right, right? If you have a left tail hypothesis, that means you need to go to the standard normal table to find the probability to the left of your z-test statistics. If you have a two-tailed hypothesis, that means what? That means you need to care about the two tails, right, of your z-test statistics. Exactly the same. Once you have the z-test statistics, you go to the normal table, find the corresponding probability to the left or to the right, depending on what kind of hypothesis you have. All right? And then that will be your p-value, right? It will be exactly the same for the two sample test. Once you have the z-test statistics, then you can find the p-value based on your z-test statistics. The only difference is for the t-test statistics. Okay, remember that for the t-test statistics, when we have in the one sample test in the previous chapter, in the last chapter, we say to find the p-value, we need to go to the t-table to find the degree of freedom, which is n-1, and then focus on this line to find your t-test statistics is between two values, go up, find the range of your p-value. Is that right? Okay, now we have two samples. That means we have N1, we have N2. So what will be our degree of freedom? Of course, it will not be just N-1, right? We have two sample sizes. That means here we have a big formula to find or calculate the degree of freedom. Right, so the degree of freedom is based on not only N1, N2, it's also about the sample standard deviation 1, sample standard deviation 2. Right. Don't get afraid about this big formula. I will not ask you to waste a lot of your time to calculate this, right? Anyone can do this job, not statistics. All right, so you can either use calculator, JUMP, or software, but in our course, I just generate, if you check your module 2 page, and under the class notes, there is one called the degree freedom calculator. Right, I just create a function in the Excel so that you just need to enter what is the value for the sample standard deviation 1, what is the sample size 1, what is the sample standard deviation 1, sample standard deviation 2, what is the sample size 2, and then the degree of freedom will be just calculated for you. Right, so it's just a long function that I can write. Right, so you just enter these values and then you should be able to know this degree of freedom. Is that good? All right, so you don't need to calculate this big formula. Even though you have this big formula, I just don't want you to waste your time on this. All right, then everything just changed back, right? So once you calculate your degree of freedom, right? So once you calculate your degree of freedom from this formula, right? And then you just go to the t-table, find your t-test statistics between two values, go up to find the range of the p-value. This is the only difference when you find the p-values, right? You may see that for some book or for some online videos, they use different degree of freedoms, right? So I just want to let you know, right? So some of them use the N1 plus N2 minus 2. Some of them use the minimal of N1 minus N1 minus 1 and N2 minus 1. All right. So actually, they are using not exact degree of freedom. That means your confidence interval or test or your hypothesis test may not be accurate at all. This is the maximum of your degree of freedom. This is actually the minimal of the degree of freedom. Right, so we do not use these two. Right, if you see that, you can skip that. It's not correct. Right. Okay, so we need to use the exact degree of freedom to get our accurate result. Right, so after we get the p-values, again, everything is the same. Once you have the p-value, you compare with the significance level alpha, all right, and then reject your null hypothesis, or you do not reject the null hypothesis. You have your enough evidence to support your claim, or you do not have enough evidence to support your claim. Exactly the same. Right. So now let's review a little bit for the hypothesis test. Right. We say the idea is the same, right? The idea is very similar. We just convert our idea to a similar hypothesis, right? So that we have a similar format of what we learned before. Right, so that means we have the right side, which is our claimed value. The left side, we change to the difference between the two population means. Right, we call the difference between these two population means as delta. Then we just call the claimed value as delta 0. All right, and then for the assumptions, since we have two samples, then we have one more independent assumption to check. And in the test statistics, since we have two samples and we are testing about the difference between the two samples, then the formulas will be, of course, will be different. But once you calculate the test statistics, everything changed back to the chapter 12. Right, so that means once you have the z-test statistics, the way to find the p-value using z-test statistics or the t-test statistics will be exactly the same. Only the only difference is for the degree of freedom of the t-test statistics, you need to calculate by this formula. Right, once you have the test statistics, exactly the same, right? Exactly the same rejection rule. All right, any questions? Not hard, right? It's just easy to understand. All right, again, once we're done with the hypothesis test, we also need to talk about the confidence interval about the difference. We say, what if I don't have my own claim? I just want to know what is the range for the difference. Right, then I want to know the confidence interval for the difference between the two population means. Right now, you should be very easy to understand this formula and this formula, right? So we say for the confidence interval, we have the general format, right, which is the estimate plus minus the margin of error. Still remember? Right? So now we want to get a confidence interval for the difference of mu1 minus mu2. We say what we can use to estimate our mu1 minus mu2. Of course, we will use the difference of the sample means, right? So we call it is y1 bar minus y2 bar, right? So this will be the first part, the difference of the two sample means to estimate the difference between the two population means, plus minus the margin of error. Still remember what is the margin of error for the population mean? We say either the z star times the standard deviation of x bar or the t star times the standard error of x bar, right? So that will be the margin of error. Again, similar idea. We say for the confidence interval of the difference between the two population means, the margin of error is still either z star or t star. We say when the population standard deviation sigma 1, sigma 2, both given to you, then you use the z star. All right, times the standard deviation of y1 bar minus y2 bar. What is that? We have already talked about that in the hypothesis test, right? It's the summation of the two variations. Got it? Right, so that will be the formula when formula for the confidence interval of the difference between two population means. We use the estimate plus minus the margin of error, where the standard deviation of y1 bar. Okay, so here be careful. This is the standard deviation of y1 bar, y2 bar, right? So this is a notation. This is not the standard deviation times y1 bar minus y2 bar, where this standard deviation of y1 bar minus y2 bar equals to square root of sigma 1 over n1, sigma 2 square over n2. So together, right? That's why I don't like this kind of formula, because it will confuse you, right? So put them together, it should be plus minus z star times square root of sigma 1 square over n1 plus sigma 2 square over n2. Right, so again, this part will be your margin of error. This is your estimate. So we have the estimate plus minus the margin of error. Right. Similarly, we say if sigma 1 or sigma 2 or both of these two are not given, what we have? We do not have the z star anymore. We have the t star instead. Right? So that means our formula will change to the difference between the two sample means plus minus the t star times the standard error of y1 bar minus y2 bar, which is s1 squared over n1 plus s2 squared over n2. Got it? So again, this is the estimate, this is the margin of error. Right, so now it's time for me to ask you some questions, right? How to find the z star, how to find the t star. Still remember? In the confidence interval, we call these two are the critical value, right? This is the critical values. Right, now let's focus on z star. Nico, what is the z star for 90% confidence interval?
1.645.
1.645. Perfect. Thank you. Noah,
Yes.
what is the z star for 95% confidence interval?
It is 1.960.
Perfect. Good. All right. Phoebe, what is the z star for 99% confidence interval?
2.576.
Perfect. Good job. Thank you. All right. Next, about the t star. How to find the t star? What information do we need? Olivia, how we can find the t star?
Is the T star bound from degree of freedom?
Degree of freedom, what else?
And then degree of freedom is the sample size minus 1. And then
Degree of freedom?
I was trying to figure out the T star.
Alpha over 2. Right? So actually to find the t star, we need both of these two information to go to the t table. right? This direction to find the T star. Okay, so again, we say degree of freedom, not n minus 1 anymore. Remember, we have a big formula to calculate the degree of freedom. So this degree of freedom is from the big formula that you can enter from the Excel and then get the degree of freedom, right? Remember, it is not n minus 1 anymore. We have two sample size now, right? And then combine our alpha. So what is alpha again? 1 minus our confidence level, right? So we say don't get confused with T star and t-test statistics, right? Normally when you do both questions in the same exam, you will get confused, right? What is the T star? We use the T star for the confidence interval, right? The t-test statistics is used in the hypothesis test. We use the t-test statistics to find the p-value. The t-test statistics is calculated from the formula. The t-star we used in the confidence interval is from the t-table, right? So for example, let's just review a little bit. I see your confusing face. Right, so let's say go to the T table. Right, so for example, let's say if my degree of freedom is calculated as 61. All right, and then I want 90% confidence interval. What is your T star? So Nancy, what do you think? How to find the T star?
You go across from 61, and then from 0.1 divided by 2.
0.1 divided by 2 is 0.05.
5.
Right?
Yeah.
Okay.
And
That
then
would
you
be,
get
so that is the T.
1.67.
Perfect. Good job. Right? So this is the T star. Right? Let's review a little bit. For example, in the hypothesis test, now we are talking about hypothesis test. Again, your degree of freedom is 6 to 1. And then you have the t-test statistics equals to 2.35. How you can get the p-value? We say once we have the t-test statistics, we focus on the degree of freedom line 61 and see 2.35 is between these two. Then we go up. This is your p values range. Got the difference? Right, don't get confused. All right, okay. So this is the way how you find the T star. We say we combine the degree of freedom and alpha over 2, and then go to the T table, find the corresponding T value. All right, so now let's come back. We say once we have our confidence interval, the last job for us is interpretation. Right? So we need to tell people, tell your manager, tell your customer, what does this confidence interval mean? Right? So here it will be a little bit more details, right? Because what? Because once you have a 95% confidence interval, for example, 95% confidence interval for the difference of the mean weights for men and women in Ohio is given by 10 to 15. What does that mean? We say the difference between these two is given by 10 to 15. First, this confidence interval is a positive confidence interval, right? So that means what? That means the man's weight should be larger than women's weight. By how much? By 10 pounds to 15 pounds. All right, then the complete interpretation should be, we are 95% confident that the mean weight for men is higher than women in Ohio by the amount of 10 pounds to 15 pounds. First, you need to specify who is larger. Larger by how much? Larger by the amount of your confidence interval. All right, so this is the way how you make interpretations. Again, similarly, but totally different order. If my difference, the confidence interval for the difference is for mu of women minus mu of men, that means your confidence interval will be a negative value. It will be a negative confidence interval. Then what does that mean? Can you just say, show to your customer, say, okay, I have the difference between women and men is negative 15 pounds to negative 10 pounds. Does that make sense? Of course not, right? Why a weight can be a negative pound, right? Then you need to be careful. We say if you have a negative confidence interval, that means what? That means your women's weight is less than men's weight by the amount of change to positive 10 pounds to 15 pounds. Right, so if you have a negative confidence interval, that means your first mean is less than your second mean by the amount of a change to positive confidence interval. Right, so that means what? That means the order matters. When you make the difference, make sure what is your order of your difference. Mu of men minus mu of women is different with mu of women minus mu of men. All right. So next, let's just go through our first example at the beginning of today's class, right? Still about the system A, system B, right? So we say we collect two samples and then with this information. One is for system A, one is for system B, right? So in my question, I don't care whether the A is larger than B or A is less than B or not equals to B. I only, what I said. Okay, I don't care how much A is larger than B by what amount. I just want to compare these two, right? I just want to know whether A is larger than B. So in this case, I just want to compare these two systems. I just want to know whether the mu1 is larger than mu2, or we say mu A minus larger than mu B, right? So in this case, if I subtract the mu B to both sides, my hypothesis will change to mu A minus mu B equals to 0 or larger than 0, right? So I just want to know whether A is larger than B. In your essay assignment, you will have another example like not only compare these two populations, I want to compare A is larger than B by some amount, right? We will do the essay assignment together next class. Right, we will have enough time to do that. All right, so now we just want to compare these two populations. And then we want to conduct a hypothesis with alpha equals to 0.01. Next, once we state the hypothesis, next step, check the assumptions before we calculate the test statistics, right? So remember, for two sample tests, we have three assumptions, right? The first one, independent assumption within each sample. That means we need to check both samples should be randomly selected. Both samples are less than 10% of their population sizes, right? So we say what? We say they randomly selected samples, right? So both samples are randomly selected, checked, right? And then we say it's in the smartphone market. So of course the users population will be very large. So of course the 10% condition will be met because the market is large, number of users is large, right? And then next one, another independent assumption between the two groups, between the samples. You need to think about it, right? Okay, can we check this independent assumption? The sample from system A, the users in system A is independent of the users in system B or not? Should be independent, right? The users should not have any relationship with each other, right? So that means this independent assumption is checked, right? So this is checked, this is checked. The next one, normality. That means we need to make sure both sample size should be larger than 30. So we have sample size, which is the number of users, 55 larger than 30, 57 larger than 30, right? So both of these two larger than 30, checked. All right, so once we check the assumptions, we can calculate the test statistics by formulas. And here we need to decide, since we are testing about the population means, we need to decide you have t-test statistics or z-test statistics, right? We have two options. So which one? Which one do we use, Rabi? We have t-test statistics or z-test statistics.
Would it be the t-test?
Would be the t-test because the population standard deviation are not given, right? Thank you. All right, so now we have t-test statistics. We just go through the formula here. Right, for the t-test statistics, we need what? We need YA bar minus YB bar. We need this third 0. We need S of A, we need S of B, we need N of A, we need N of B. So what are they? Let's look at our information table here. Right, so let's say Dominic, are you there?
Yeah, I am. What was the
Okay.
question?
I haven't asked yet. All right,
Okay.
so what is the notation for this 13?
13, it's mu of A. Is that it? Mu of A? Mu of 0. Or mu of A.
Again,
Mu of A.
try again. Think about what is this. Okay, this is the mean, right? This is the sample mean or the population mean.
Oh, it's the population.
This
Sample.
is the sample, right? So this
Okay.
is the
Oh, it's
from
8.
both sample, right? So this is the sample mean. Then what is the notation for this sample mean?
H0. I don't know.
Okay, that's fine. No problem. Cole, what do you think? Cole?
Yeah, to be honest, I have no clue as well.
Okay, so let me repeat the question again. All right, we say we want to compare the two population means, right? And that's why Vivian randomly selected two samples, one sample from system A, one sample for the system B. So one sample has 55 of them, one sample with 57 of them. Right. Then my question is, what is the notation for this 13? What is this 13? Any idea? Any volunteer?
Is it Y hat A?
Excuse me?
Y hat A?
Right. So this is actually it's Y bar A, right? So this is the sample mean of A. Right? So this is the Y bar A, or you can call it as X bar A, it doesn't matter. All right. Similarly, this 10 will be Y bar B, right? So this is the sample mean of B. Okay, next question. What is this 5? Maria?
SA.
SA, right? Perfect. Good. Right. So again, this will be SB. This is the sample standard deviation S, right? Perfect. Good job. All right. Next one, the number of users, 55. Marie. Marie?
NA.
NA, right? Okay, perfect. NB. All right, so now you figure out for every value, what are they? Then what you can do, just plug in the values into the formula, right? So we say we have Y bar A as 13, Y bar B as 10, and then SA is 5, NA is 55, SB is 3, NB is 57, right? The only thing you need to figure out is this delta 0. What is this delta 0? We need to go back to our hypothesis, right? So we are testing about 0. So this is our delta 0, right? This is our claimed value in our hypothesis. All right, so that means in this formula, you have everything in this formula. Just calculate the value as your t-test statistics. Right? Okay, so once you have the t-test statistics, next step, find the p-value based on your t-test statistics. Right? Okay, so again, to find the p-value based on your t-test statistics, how we can find it? Let's just think about it before we go to the t-table, right? So we have degree of freedom for the t-table. We need to first fix the line of our degree of freedom and then see our test statistics is between two values go up. We will find the range of our p-value. Is that right? Okay, so now we have our t-test statistics ready as 3.833. The only thing left is to find our degree of freedom, right? Okay, so how we can find our degree of freedom? We go to the Excel, right? Okay, and then we just enter whatever information we have. So we have S1, which is 5, right? We have N2, which is N1, which is 55, S2, which is 3, N2, which is 57. All right, so that means our degree of freedom will be 88, calculated by that big formula. All right, so now we know the degree of freedom equals to 88. we need to just focus on 88 line and then see our 3.833 is within what range, right? Okay, so let's go to 3 point. Okay, erase that. Right. So we say our degree of freedom now is 88. We have our t-test statistics from last step is 3.833. What is your p-value? Try to find it by yourself. We'll focus on the degree of freedom, 88, right? What is your p-value then? What is the range of your p-value? Ben, what do you think? Ben?
Yeah. So the range of the p-value would be less than 0.0005.
Perfect. Good job. All right, so we say we have the t-test statistics is 3.833, which is even larger than this 3.405, which is should be somewhere here, right? To the right of 3.405. Then if you go up, that means your p-value should be to the right of this 0.0005. And then you can see these values 0.1, 0.05, 0.025. That means to this direction, the p-value getting smaller and smaller. That means to the right of 0.005, 0.0005 should be even larger than your p-value. Your p-value should be less than this 0.0005. Get it? Repeat again. Right, so we say based on the big formula or our Excel, we say we calculate the degree of freedom is 88. So we just focus on this 88 line and then see our test statistics 3.833 is actually even larger than 3.405. That means your p-value go up. Your p-value should be even less than this 0.0005. Right, so now we are done with the next step. We got the p-value is less than 0.005. Then here should be 5. Then what? Then the next step, make the conclusions based on the p-value and alpha, right? So we say we want to make the hypothesis test with the alpha equals to 0.01. So we say, since your p-value is already less than 0.0005, so of course it is less than alpha, right? Less than 0.01. So what is our conclusion? We reject the null hypothesis, right? We do have enough evidence to support our claim. What is our claim? Our claim is, we need to check our claim, which is our mu A is larger than mu B, right? So that will be our conclusion. We say we have enough evidence to support that the users using system A should spend more money on the app than the users using system B. So kind of expand what does this mean in the real practice. All right. For the next, let's just do it next question quickly, right? So we say we still use the same sample, still about the system A and system B. Right now, I want to get a 95% confidence interval for the difference, right? So again, first step, we need to check the assumptions, right? Since in the last question, we have already checked the assumptions, so we can go directly to the formula, right? So we have all the information, YA bar, YB bar, and standard error, which is the SA, SB, NA, and B. We all have these information, right? The only difference is we need to find the T star, right? Still remember how to find the T star? We need the degree of freedom, alpha over 2, right? So that means we have degree of freedom calculated as 88. We want 95% confidence interval. That will be 0.05 divided by 2, which is 0.025, right? So we need to combine these two information to find the T star from the T table. Right, so that means we need to focus on the line of 88, combine with T of 0.025, go down, right? So that means your T star will be just a 1.987, right? So once you got the T star, you just plug in into the formula, everything is done, right? So you just calculate your confidence interval, and then we have the interval format, right? Okay. The last thing I want to talk about is once you have the confidence interval, how you can interpret it. Again, we have a positive confidence interval, right? This is about the difference between mu of A minus mu of B. It is positive. That means A is larger than B by this amount, right? So when you interpret it, that means we are 95% confident that the users using system A spends averagely more money than the users using system B. So this explains why it is positive, because A is larger than B. By what amount? By the amount of 1.445 to 4.555. Right? So in this case, what? In this case, we say that users using system A spend more money, so Vivian can make the decision to build the new features on system A. Then we are done. Right, so next class we'll get a review for today's class, and then we will talk about the jump, and then we'll give you time to go through your essay assignment. I just since we have the time, then we can just give you the time and do the assignment together, and give you more time for your data analysis 1. And also we do not have class on next Wednesday, so see you on next Friday.